you can do it with in the medical field, or in econometrics, or in the social sciences. So there's really never just one definition of something. It's more like a concept that then has to be adapted to many different things, and there are many different perspectives, I would like to say, to understanding certain concepts in statistics, which always also depend on the knowledge of you as the expert, you as the medical doctor, or someone else as the econometric. So we always, as statisticians, we always need collaborators to help us understand what we're actually doing, and then to give us kind of the knowledge to go ahead and really bring kind of knowledge and purpose to the statistics that we're applying. Just as a heads up. So if you've heard some things, but they've been defined differently, it might very well be either to be traced back to the different understandings of statistics, or because I made a mistake. That's also possible. Okay, so let's dive in here. So what I thought we could talk about is first a little bit about statistical testing. So like, okay, how do I transform a scientific question that I might have into a statistical test, and especially a statistical kind of hypothesis that I can then go about and quantify and test and like get some reliable result for. And then the second bigger question would be sample size, and of course, what is power? What do we have to kind of understand underneath the big word power? And then secondly, we could talk a little bit about simple linear regression, like what is linear regression, how can we interpret in linear regression, and then what are some pitfalls. So let's dive into statistical testing. Let's assume we are all doctors, even though I'm not, and we are interested in measuring how much blood pressure across the ages 30 to 85 is reduced by a treatment with statins. And I just Googled that. That's how I found out that statins reduce blood pressure. But, the example might be might not make much sense to you, because how blood pressure actually behaves, but like, just bear with me, it's a theoretical example by someone who does not have much knowledge. Perfect. And so like this is our scientific medical question that we have, and now the big question is, well, how do we go from this like expert knowledge to a statistical hypothesis? Well, first of all, say we have all the resources to conduct an ideal randomized trial. So say we have participants who are here, who've been kind of randomly sampled out of the study population that we're interested in. They fit our criteria of being aged between 30 and 85. We randomly assign them a treatment. So one group gets a placebo, the others get statins. The groups are exchangeable. So like the covariates, their socio-demographic variables are roughly distributed the same way, meaning the groups are kind of the same. And if I apply the placebo treatment in the statin group, I would get the same result as I got in this placebo group. And we can measure kind of the average blood pressure for each group, and each group has, say, a sample size of n. We just use n as our like variable or our fixed group, but I just didn't put a number behind it. It could be 100, whatever. So we measure the average blood pressure, and say then we compute we measure the blood pressure for each person, and then say we compute the average. So we have an X bar, which we use to denote the placebo average blood pressure, and a Y bar for the statin group. And then, as I said, we're interested in how much the treatment with statin changes our blood pressure. So we just compute our delta, which is a common way of mathematically denoting a treatment effect, delta. And it's nothing else than kind of the average blood pressure of the placebo group minus the average blood pressure of the statin group, to kind of, to figure out, okay, how much does it differ? Great. So then we know now we have like a mathematical notation, the delta, and a mathematical way of computing our metric or the variable that we're interested in, the difference in average blood pressure. And now the question is, well, how can I now express this question or this hypothesis, it's lower, in a statistical way? The thing about hypothesis testing, many of you might have already come across that, is that we have two different hypotheses. We have a null hypothesis denoted by this H0, and we have an alternative hypothesis denoted by an H1. And we always need to put our research hypothesis, so the thing that we're kind of interested in proving, we put this into the alternative hypothesis because, and that is really fundamental to any sort of statistical test. And if you take away one thing from this presentation, it is that we can never accept the null hypothesis. All we can do is reject it. We can reject it. We can say, no, it's false. But we can never say, oh, it's true. And that's just the way how a statistical test is like constructed. We control for an error term, but we cannot control for like the right term. So in the end, what I'm trying to say is that even if we know that the null hypothesis, that and in this case, our null hypothesis would be, oh, statins have no effect on blood pressure on average whatsoever. So our delta, we expect our delta to be 0. Whereas the alternative hypothesis is, oh no, statins have a positive effect on blood pressure, meaning they reduce blood pressure. So our delta would be positive, would be greater than 0. And so this, even let's say the delta would be really null, so statins do not have any effect on blood pressure, the average blood pressure. We don't really know how our test statistic would behave, or all we can say is, well, we have some sort of it's controlled on how often we then still reject our null hypothesis, but not how often we accept it. So that's kind of why you can only reject, not accept the null hypothesis. Good. Just quickly pausing in case there is any question here. Otherwise, I will move on. So we already talked about what this means in words, basically. Okay, great. So now, in order to kind of further move on, we now have our hypothesis, we have a metric on how to measure, and now the big question is, well, what else do we need? And the big thing about statistics, we always need assumptions, because otherwise, if the world is too uncertain, we freak out and we're like, oh no, but we don't know what to do now. And so what we know kind of from measurements is that blood pressure is kind of normally distributed. So that's this classic bell-shaped curve that you've probably seen many times. And for every person, we assume that, disregarding, obviously there's a gender difference in blood pressure, but we can disregard that for a moment. For every person, kind of the measurement of blood pressure is identically distributed. So they all come from the same bell-shaped curve. Obviously they're different, but kind of the underlying pattern of them would be the same. And they're all independent. So my blood pressure wouldn't influence my friend's blood pressure measurement. So we kind of write this in a statistical sense as this X wiggly sign N, where N is kind of the short term for saying, oh, it's normally distributed. And we have an average mu, that's this weird U, and a sigma squared, that's our variance. And under the null hypothesis, given that we assume delta is 0, we know that X, so the blood pressure measurement in the placebo group, has the same mean as Y, the blood pressure measurement under the statin group, because there's no difference between the two statins. Right under the null hypothesis, we think that, oh, it doesn't have any effect. Great. So let's move on and let's get to the the important things, the one-sided t-test, which is a very common way of testing now, actually statistically putting some evidence to our hypothesis. And so we construct this standardized statistic, this called t-test, which, and the important thing is, we know its distribution, which just means we know how it should behave given our null hypothesis. Because, right, our null hypothesis told us, well, delta is 0. So based on that and our assumptions about normal distribution of our measurements, we can now say, okay, so if I construct this t, which just measures the difference between the average blood pressure measurement in the two groups, so under the placebo and the statin treated group, and divide that by this expression, so 2 times the square root of sigma squared, so the standard deviation, but we'll touch on that later a little more, divided by the square root of n, we get a statistic that is normally distributed. So there's again the squiggly line n. And that'll help us, because that way we can actually make statements about probabilities, because we know kind of how this t should be distributed, what its normal values are for our null hypothesis. And now if we insert our measurements and we get a t that looks really weird, a t that we wouldn't expect, we can then come to a conclusion of saying that, oh, well, our t looks so different, it looks so extreme, we wouldn't expect that under the null hypothesis. So maybe our null hypothesis, delta, is not equal to 0. Maybe statins do have an effect. And that's kind of like the process really across different statistical tests. It's not just the t-test, but many different, or all the statistical tests that kind of work with that rationale of checking whether or not my value makes sense, or if it doesn't make sense. And if it doesn't make sense, it tells me that, oh, one of my assumptions must be wrong, i.e. that the assumption of my hypothesis must be wrong. And then I can reject the null hypothesis and say, oh, well, very obviously it's not true. We have to decide we can accept the alternative hypothesis. And another thing that you will probably notice here is that the sample size, n, plays a very important role, because it decides, or it determines how our t is spread, which means like how wide the range of possible and like purposeful t values are. Good. So as I promised, touching back on this big standard deviation, standard error, you probably heard both. They are related, but they're not the same thing. So a standard deviation basically tells us, it's defined as kind of the square root of the variance for a single measurement, which is not very intuitive. But if you think about the variance kind of tells you how much your values spread across your range of values, how variable is your measurement. So say for blood pressure, for example, well, people, obviously, we all have different blood pressure values, right? But for a healthy individual, there's a certain range that your individual blood pressure, that my blood pressure right now, if you measured it, where should it be? What is healthy, kind of? And where would normally, if you measured me today and the day after and the day after, like there's a certain range that my blood pressure would always fall into, right? And so that is kind of, that is just what the standard deviation describes for us. And it's statistically very often denoted as the sigma, because we describe the variance is sigma squared, and so the square root is just sigma. Then the standard error, that is the square root of the variance of the average difference in measurement. And so I think after understanding, well, okay, what is variance in general, then it's pretty easy to understand the difference between the standard deviation, standard error, because it's just a different type of kind of measurement that I compute the standard deviation from. We just use a different name for it. So the standard error would be as I said, the kind of the average range that the average blood pressure measurement would fall into. So say you wouldn't just measure me every day, but my group of friends, and then kind of compute an average blood pressure for every day that we were observed. Then kind of the range in which this average value falls into would be, or the spread would be described as, or would be, the standard error. And in our case, with our like x bar minus y bar, this is just the 2 sigma divided by square root of n. That's how we can compute. And very obviously, you see that the standard error depends on the size of group of friends I have. So the larger my group of friends, obviously the more representative of a bigger population, and the more certain we get that, oh, this average that we are compiling, well, it's based on more and more people, so more and more information, and we can very much assume that it is kind of representative, and hence the spread of the values also becomes smaller, because we have more and more people, which just lead towards a focus on the actual average blood pressure that we know of for our population. Yeah, so as I said, the larger n, the more narrow kind of the spread, and you can see this really nicely in this graph. So the really high peaked ones has the largest n, and hence kind of the curve just shrinks together, because we just become more concentrated on certain values. And with regards to our t-test, it just means that the larger our sample size, the more certain we can be that our t value must lie within a very small range. And so if we do have deviations from the null hypothesis, it'll become more sensitive to picking this deviation up from and to actually tell, like, we just become more certain, and we know that even if delta, our statin treatment, has only a very small effect on the blood pressure, we will pick that up. As we increase sample size, we will pick that up with higher probability. So the big question now is, well, yeah, obviously the larger my sample size, the better. So why don't we just, go ahead and ask as many people as we can possibly can? That would be nice, and we statisticians would maybe not even be needed anymore if you can ask just everyone, because our work would become redundant. But the thing is, as you all know, we can't just ask everyone, because it requires cost and it requires a lot of effort. And very often people are like, for surveys or whatever you want to do, they're unreachable. We can't actually reach them because they won't participate, or because they live very remotely, or because they just don't want to participate. So there's always a trade-off, right, between, well, I need to find a sample size that is large enough in order for me to make substantial claims and do proper statistical analysis. But on the other hand, right, I work within a tight budget, and I need to find something that it has to be big enough, but not larger, because I don't have money to spare very often, or I don't have time to spare, or whatever it is. So in the end, we just need enough information to not make, and that's the main point, to not make mistakes more than a certain number of time. That's kind of how we define this. Well, it has to be large enough, because that's what we're mainly interested, right? If the null hypothesis, if statin really does not have an effect on blood pressure, we don't want to, based on our statistical analysis, all of a sudden believe that it does have an effect, right? The FDA wouldn't want to see that, you claiming that, well, yes, my treatment has an effect, but in reality it doesn't, and you just prescribe drugs to patients without those drugs having an effect, but you make them believe they have an effect. I mean, that just doesn't work. So we need to make sure that we don't make a mistake in claiming that something has an effect too many times. Obviously, we can never be certain because we couldn't check everyone, but there has to be an upper limit. And this limit, this like error probability, is called the type 1 error. So if we assume our null hypothesis is correct, statins have no effect, we want to falsely claim that they do have an effect with a probability that's smaller than alpha. And it is established to use alpha 0.05 for a one-sided test or a two-sided test. So how exactly does that translate into a test scenario? So as you can see down here in this graph, you have the distribution, as we already talked about, of our t-value under the null. So how does it normally behave? What would we expect? What kind of values would we expect, given that our treatment has no effect? And then there's like this upper red tail, as you can see. And this is for us, well, okay, so we're interested in having a delta in checking whether or not, well, does statins really, do they not have an effect, or do they maybe have a positive effect? So is the delta maybe bigger than 0? And so that's why we look at the right upper tail. And here the big question then is, okay, if I like determine this cutoff at 1.645 for my t-value and say that, well, if this value of t is larger than 1.645, we can assume that our null hypothesis is wrong and our alternative hypothesis is true, and that statins actually do have an effect. And by choosing this cutoff value, we guarantee this alpha type 1 error, because as you can see, under the null, under the assumption that statins do not have an effect, we only fall in this upper tail with a probability of 0.05. 5% of the times, if I created t over and over again on average, we would only fall up there. So it's very unlikely, if statin really don't have an effect, to get a t that's that extreme. And so that is kind of the reason why we can say, okay, well, while we might make a mistake, it's very unlikely for us to make a mistake. So we can be pretty certain. And we can that way construct this cutoff value, which will allow us to actually decide, okay, do we now reject or not reject our null hypothesis? And another concept that you might have heard of is the p-value, which is just the probability for to get a t which is more extreme. And so if based on my current observed t value. And so say that I have a t value that I measured my blood pressure across my groups, and I computed the t, and the t is larger than the cutoff, larger than 1.645, then the probability of being even more extreme under the assumption of the null would be less than 0.05. And hence, this is why we kind of test based on the p-value very often, which just says that we reject the null hypothesis if our p is smaller than alpha, because that means we lie within that right red colored tail region, which is very, very unlikely. And so we can say that, okay, well, it's so unlikely that we can reject the null and say that actually we don't believe the null is correct. Okay, now coming to power, and power is very similar to this idea of the type 1 error. We define power as under the assumption that the alternative hypothesis is correct, that our statins do have an effect on blood pressure. We want to make sure obviously, that we only reject the null hypothesis with a very high probability, because obviously if our alternative hypothesis is true, we want to make sure that we decide for it, and in order to decide for it, we need to reject the null hypothesis, and that's where power comes in. So in order to proceed to obtain 80% power, we kind of need to make sure that our beta only is 0.2. And beta here is the so-called type 2 error, which again, we can compute based on this cutoff value of 1.645. And we just, as you can see from this like second line, so the blue line is the line that we had before, right? And you have the 0 and you have our 1.645, the threshold, and then you have the alpha. That's just like the picture we looked at before. But now you have an additional curve, which describes the true alternative hypothesis. So this curve is shifted. And now you can see in this case, the red highlighted region would be the region in which because we lie below the threshold, if our t had a value within like in that red area, we would actually not decide for the alternative hypothesis. We would not reject the null because it lies below our threshold. And so in this case, the beta marked area describes the probability with which we falsely assume there's no treatment effect, even though there is a treatment effect. And the power, on the other hand, would be the white area. So that would be everything above the threshold, because that's when we correctly assume or conclude that our alternative hypothesis is correct. So yeah, this up here is the power. And so now, obviously, as we said, we want to make sure that our power is high. We obviously want to make sure that if it does have a treatment, we detect that treatment. So how can we increase power? So one thing is, the bigger the difference between the null and the alternative hypothesis, the larger the power, which might sound a little weird, because how can you increase the difference in your null? It just tells you that, well, the higher the actual effect of statins is, the more likely you are to also detect it. Obviously, the stronger the effect, makes sense, right? That the more often you would actually detect it in a statistical test. Then obviously, if we increase the type 1 error, our threshold moves to the left, and we can easily see in this picture that then the red marked area would decrease if I moved my line to the left. However, you might also notice that then the blue marked line would, or the blue marked area would increase, which means obviously our type 1 error would increase, which is also not great, right? Because it means we make false positive claims. Then we could decrease the variability in our data, which can be done sometimes, might not be done, be able to achieve if we look at blood pressure, because I mean, there's just a certain way that we measure blood pressure, and there's a certain variability between people. There's nothing we can do about that. But the biggest point is actually changing sample size, because as I told you, right, the larger the sample size, the more narrow our curves get. And so if we imagine more narrow curves here, we can easily see that the red and blue marked area would decrease. So we can kind of increase power and decrease our error rates that way. Okay, so after a lot of talking by me, let's bring all of this together. How do we, in the end, like based on all this new knowledge, how do we compute the sample size? Well, first, let me say one more thing about before we get to the nitty-gritty. Sample size always obviously has to be determined prior to the trial. It is something that you usually go to the FDA with and tell them, okay, so this is the sample size and this is what we want to do. They won't accept if you change samples or if you've not set a sample size. You always need to give them a value for your sample size. And so we kind of have to determine sample size a priori to measuring any effects. And usually you do that by assuming a certain treatment effect. Obviously, we know statins, we know how they work in people's bodies. So we might have a realistic assumption of what this effect delta should be. Say, based on literature review, I figured out that, well, probably it will decrease my blood pressure measurements by X. And that then, based on this assumption, you will compute the sample size. And so here I gave you like the formula on how to do it. It's based on the alpha, so the type 1 error, the 1 minus beta, the power. So both of these desired properties, I want to only make mistakes with a probability of alpha, and I want to make sure to properly make a proper conclusion with a probability 1 minus beta with the power 1 minus beta. That's both of these kind of desired properties go into the calculation of sample size and our standard deviation and our assumed treatment effect. And so back to the statins, let's say that we aspire to measure a decrease of delta equals 2, say that we assume based on literature review that statins decrease our blood pressure measurements by 2 compared to the placebo. And let's say we know because we've measured so many people, measured the blood pressure of so many people, that our standard deviation, like how much do blood pressure measurements deviate from person to person, is 15. The quantiles we can look up in tables or we can Google for them. It's very, very easy. They're just the standard normal quantiles for alpha 0.05 and a beta of 0.2. And then we compute that, well, our minimal sample size to detect such a delta equals to 2 is 73. So we would need 73 participants to kind of measure the effect of statins. And yeah, so far so good. That's all I had for power and t-statistics. I'm just going to pause here for a moment in case anyone has a question.
Participants are welcome to ask questions via the chat box, or you can raise your hand. Please do. If you have any lingering questions for Stephanie, do not hesitate.
Also, if you didn't understand something, I'm more than happy to try and re-explain in a different way.
I think not yet, Stephanie. I think we'll have another discussion session at the end of the presentation.
Perfect. And let's dive into simple linear regression. I will try to make it a little shorter, since you've been listening to me for way too long. Yep. Oh, wait a moment. We look at the power of marketing. Sorry for not making a medical example, but I thought maybe we should widen our horizons and think a little bit about marketing, since it applies to every one of us. So simple linear regressions are a way of, or regression is a way to detect a linear relationship between variables. And so very often we're interested in, say, predicting something based on something else, which, yeah, obviously makes sense, right? We have a lot of uncertainty in this world, but we know that certain things kind of, they are related. So why not use this relationship to predict than a certain value. And that, for example, became very, very important during COVID, right? We had, for example, different metrics, and based on these different measurements, we could, for example, compute, okay, what's the incidence of COVID going to be like tomorrow? And we can maybe explain that based on, well, the incidence today, plus maybe some sort of information on, well, what kind of restrictions are in place right now. And that'll then help us to make policies. And that is really, really important. And that's kind of the whole purpose behind regression. And simple linear regression is just the most basic and most fundamental version of it. So here we have, obviously, if you invest a different amount of money into your marketing ads, ideally what you'd hope is for your revenue to pick up, because people know more about your product and so on. And then we can assume maybe that the relationship between this marketing investment and the revenue is ideally linear, which means that we can just describe it by putting a ruler on top and like drawing a straight line, and that'll give us a good approximation of this relationship. But what this relationship exactly is and how we can compute it, that's kind of the business of simple linear regression. We have one dependent variable, the output variable, which in our case would be the revenue, and we have would be the revenue, and then we have one independent variable, which is our input variable. In this case, it will be our marketing investments. So as I said, it assumes kind of a simple linear regression assumes a linear relationship between these two variables. And here we have a good example of something that would not be a linear relationship, because we can't just take a ruler and draw a line through it, but it's more a curved line that we need to describe the relationship. And as you can also see from this page, obviously or slide, obviously we always have to do with error and noise in statistics. We sadly never get a perfect measurement. We can never really measure 100% the underlying relationship, because our world is loud, and so we have tons of little influences on our measurement, on our measurements, and so we only get like this squiggly plot of many different points, and they might be scattered all around, which is why this plot is also called a scatter plot. But we kind of want to find a simplified either a curve or a linear line, an actual line, to describe the underlying relationship if we forgot about all the noise that influenced our measurements. So and ideally, obviously, in simple linear regression, we're looking for a linear line between the two. So a linear relationship can always be described by two important features. We have a slope, which tells us how steep the line is. So if I have if I have a slope of 0, it's just going to be a horizontal line. If I have a slope, like as the slope increases, it becomes steeper and steeper and steeper and steeper. And then we have an intercept b, which just tells us like, okay, where's our 0 point, right? If I insert x equals 0, where's our y? So that's kind of we could imagine it a baseline revenue that I would get if I invested 0% into marketing, because obviously people will come across my product in the store and be like, oh, this is a nice product, I want to buy it. Or we would have in medicine as well, right, a baseline value without any treatment. You have a baseline value. And so now coming back to our example, we have these like plots these points that we've measured, and we now want to detect, okay, so how do I have to draw this line to explain the linear relationship that underlies underlies our observations. And there are many different ways we could kind of draw this line in between the points. Is there a question? No, just someone.
Yep. Nope. Definitely. I think it's accidentally turned on.
Okay. No worries. And so obviously, so yeah, coming back to this example, how should we create this, or how should we draw this line, right? Which one is the right one? And the black one here, that's actually the right one. And why is it the right one? So we always, as I said, we try to minimize we try to find a relationship that describes the underlying relationship without the noise. But obviously we cannot assume that, oh, our world is super noisy. We kind of have to make the assumption that we assume there's minimal noise, and we want to draw a line that minimizes this noise. We don't want, to draw a line anywhere and just say, well, yeah, this is the real relationship, and we assume everything else to be noise. No, we're kind of optimistic. We say, so we measure things as good as they come, and we assume the noise to be really minimal. We tried really, really hard to come as close as we can. There's still some noise, but we can assume that it is as small as possible. And so we need to draw this line and to detect the real relationship as closely as possible to the points, such that this kind of difference between what the line would tell you and what the actual measurement is, that which is here denoted with these like red lines, that is minimal. And that is how we compute. That's like the algorithm. That's how the algorithm behind linear regression computes your slope and your intercept. So we need to find those two in such that these red lines are as short and as small as possible. So in this case here, with the marketing example, we would have an intercept of 95 and a slope of 10. Okay, so much so good. But then obviously, and I bet you've probably heard about that before, linear regression is nice and we see it works, but there are many, many ways it can be wrong. And so one of them, as I already said, very often now, is that we have noise. And while some noise is okay, and we can work with some noise, some numbers might also just be inaccurate. So you can always have outliers in your data, and those will have obviously a large impact on how you compute your regression. Then there are other variables that could influence your outcome. And so just accounting for one just doesn't cut it. It doesn't describe the relationship, the real world relationship that you have. And then lastly, your relationship might not be linear. We saw before, right? It can also be a curved one, or it can be something very, very complicated. And then just using a linear regression just won't help you much, because it won't be just won't be very accurate. Linear regression is very limited in what kind of relationships it can detect, only linear ones. So the question is, how could we improve such a model then? Well, obviously we can always, regarding our outliers, we can just leave them out. We can exclude weird values and weird measurements. Secondly, if we have, or we know that, well, maybe our assumption, our model was a little bit too simplified, we can try and include more variables in order to, and interactions between the two, in order to account kind of for a more complex relationship. And lastly, there are many, many models which model more than just a linear relationship. You can do quadratic terms or to the power of 3 terms. You can really go crazy. The rationale behind the models is always the same. We try to fit a line, some sort of line, whatever it might look like. But we always try to make the error as small as possible. So we always want to be this optimistic and say, okay, let's try to fit a more complicated model relationship, but we still think that we did a quite good job in measuring. So we have to like fit the line as closely as possible to our points. And now some fun things I want to kind of close with. The important thing about statistics in general and some regression here in particular is that in our daily business, we measure correlations, we measure associations. So the example that I showed you between marketing and revenue, if we measure that and draw the line, all that it tells us is that, well, obviously, as I investing more and achieving a higher revenue comes together. But it doesn't say anything about more investment in marketing it causes higher revenue. This kind of interpretation of causation only comes into play with sufficient expert knowledge, with like certain statistical methods that we can assume, but that have certain like even more assumptions that we can apply. And it becomes like fairly complex fairly quickly if you want to make a causal claim instead of just an associational claim that something comes with something. And just very funny examples are, you can have these seemingly causal relationships between absolutely random variables. So for example, people who drowned after falling out of a fishing boat correlates quite highly with the marriage rate in Kentucky, but neither of them is a cause to the other. It's just chance that they somehow, out of some weird reason, go together, that you somehow see this association between the two. Another very funny one is the math doctorates awarded correlated with the uranium stored at US nuclear power plants, also very highly correlated, but the one won't cause the other. Or if you look at the cheese consumption and the number of people who died by becoming tangled in their bed sheets, again, won't really have anything to do with each other apart from somehow having the same value or similar values across the years. So yeah, coming back to regression and kind of wrapping it all up, we know that a regression model cannot be interpreted as causal, but it is associational. The variables are, as I said, like associated, they are correlated with each other. And the correlation kind of, we measure the linear relationship between the two variables. And nothing more. So in our marketing example, we can say that if our investment was increased by +1, our revenue would increase by +10, because that is our kind of our slope. And so the slope always tells you how much change you expect in the outcome given a 1 unit change in your independent variable. So yeah, to put it all together and to finally make me stop talking, what a regression in a nutshell? Well, first of all, you need to identify your dependent and independent variables. As before with the power and the statistical tests, we always first need to think about, okay, what's our question? And then how can I put that into statistical terms? And while for the tests, it means putting it into an alternative and a null hypothesis. For regression, it means determining, okay, what's my outcome and what are my input variables? And then we have to consider, okay, well, are those two somehow, do we assume the two to be linearly related? If yes, we can go ahead and apply simple linear regression. If not, then we might have to look elsewhere and model some more complex relationships with other statistical methods. Then we calculate our slope and intercept. So based on this approach to minimize the error, which is also called the least squares method. And then lastly, we can finally calculate our predictions, predict what our outcome might look like for a certain input value. And that's it. Thank you so much for your attention. I hope my presentation kind of gave you a little bit of an overview. And yeah, I'd be more than happy to answer any questions.
Thank you very much, Stephanie. That was a really comprehensive and very enlightening talk on statistical testing, power analysis, errors, determining samples, and you put in a bonus there, regression. Thank you very much. Now we will move on to the discussion session. So we encourage the participants to ask questions so that we can discuss it with our content expert, Stephanie. Please feel free to ask via the chat box, or you can directly raise your hand, and also feel free to ask either in Bahasa or in English. Please do go ahead. We have around maybe 15 minutes for this, so we can get a good discussion on it. Anybody has any question? Okay, Tifa, please unmute yourself and you can ask your question.
Okay, thank you, Gracia. Okay, and thank you, Stephanie, for the really good explanation about the statistical power and sample size and etc. And to be honest, it is my first time to understand like the p-value, the power, and also how it means in the real research, because I get used to read article and it only say, oh, the p-value is less than 0.05 and it's significant, so the research is good. That's what I only knew before I watch your presentation. So you said that you mentioned about the power and how it can what is it? It can reject the null hypothesis, and you also mentioned about the sample size. So my question is, can the sample size influence the power? I mean, maybe perhaps if the sample size is increased, so can it also increase the power, or vice versa, or not? That's my question. Thank you.
Yeah, no worries. That's a very good question, and it definitely is the case, which is why sample size is such a crucial element to statistical testing. You're absolutely correct. I said right that the type 2 errors, or the beta kind of that we were talking about, the blue, or I think it was the red area. If you increase your sample size, and as your curve shrinks together, this area becomes smaller. And if that area becomes smaller, it also means that the counterfactual to it, which is the power, which is the 1 minus beta, then increases. Yeah, absolutely. So the larger, and it makes complete sense intuitively. The larger your sample size, the more information you kind of have, and hence the more certain you can be about what you're saying. And so if you then do have an effect, say, of the statins, you would be more likely to actually also detect that effect. And so your power, your probability of correctly accepting the alternative hypothesis would be larger. So yeah, you're absolutely right.
Okay, so yeah, by increasing the sample size, it can increase the chance that the alternative hypothesis is right. Is that correct?
Or that you would correctly identify the alternative hypothesis to be correct, right? Yeah, yeah, absolutely. Yeah. So Yeah, I think from you can also look at it from a different, like slightly different perspective, or like power and type 1 error. They are two sides to the same coin. So from a FDA or medical regulatory institution perspective, you always assume there's no treatment. And so, right, because that's kind of where they come from. So you need to really, really prove me that there is an effect before I actually believe that there is an effect, because taking no drug is better than taking a drug that doesn't do any good for me. And so that's why they are very much interested in this type 1 error. So how likely is it that even though there is no effect, the pharma company comes along and tells me there is an effect, right? So they want to minimize that. But the pharma company, on the other hand, is like, okay, I assume there is an effect. My drug works. I need to make sure the power is as big as possible, so that if I do my trial, that it will actually tell me, that it will prove my hypothesis, my baseline belief that there is a treatment effect to the treatment that I'm supposing. So that's then how they try to increase power. So it's kind of like two different perspectives to the same question in the end.
So type 1 error is not enough. So we should also add the type 2 error, right?
Exactly. And exactly, absolutely. And that's why the sample size, as you saw, it is based on both the type 1 error and the power. Both properties, like in the end, determine my sample size.
Okay. Thank you, Stephanie.
You're welcome.
Thank you, Stephanie. Anybody else have any questions? Any other questions? Going through the chat box. Oh, I think Ika personal chat me about a question, Stephanie, but she couldn't turn on her mic for now. Oh, sorry. Yehuda wants to ask. Okay. Please go ahead, Yehuda. Feel free.
Yes, thank you, Kak Gali, for the time for me to ask questions. Let me introduce myself. My name is Yehuda. I'm an undergraduate medical student from University of Jember, Indonesia. Nice to meet you, Stephanie. It's really a pleasure for me to hear the presentation from you. Actually, biostatistics is one of my favorite subjects in my schools, but I found myself really hard to develop my skills in these topics actually. But I'm really passionate to do research about meta-analysis methodology. So when I read some clinical trials articles, sometimes I found that some researchers choose to present their outcome data using median and interquartile range instead of mean and deviation. Is there any considerations why researchers present their data using median and interquartile range instead of mean and mean difference? Since I think that's about heterogeneity issues. But is there any reasons about that issues? Thank you, Stephanie.
That's a good question. So as far as I know, the very often the reason to kind of go for the median and the interquartile range would be to ensure robustness. As you said, if the data is very heterogeneous, and if you can assume that there might be a few outliers, i.e. Data points that look a little off to you, and I think in addition to not in meta-analysis, right, you have the problem that the data comes from different sources, so you cannot 100% ensure that it's all measured in the exact same way. So then going to but you kind of assume that it is roughly the same, or you can make sure by transforming to ensure that they kind of fall within the same range, using something that's a little more robust and kind of has a nicer property to be interpreted in this sense, helps helps just to ensure that your claims are, I guess, more fun, just more robust and more correct to a certain extent. And I mean, the median also, you can always, there's a big discussion around, do we prefer the mean or do we prefer the median? Obviously the mean has very often nicer properties, and it's very intuitive, but the median has a very nice interpretation, and especially in data that might not be 100% normally distributed, but has a few, not necessarily outliers, but just extreme values. A very good example would be income. It doesn't make sense, say in the US, it doesn't make sense to compute the mean income in the US because you have Jeff Bezos and Bill Gates living here. And all of a sudden you have a mean income of, I don't know, 1 million. But that is just not realistic, because we know that most people don't earn that much. But you just have these few outliers who are like, they're real people. They very much do have these earnings, but that doesn't help me. It doesn't have any like value to the testing of my to answering my general research question. And so I would rather choose the median, right, which describes to me, okay, which is the kind of middle point, as in 50% of my observations have a value below that point and 50% have a value above. So I think that might be one of the reasons. It could also have to do with, as I said, the research question, and that they say, well, maybe there are a few high points, but we don't want them to distort our overall conclusion. I hope that helps.
Yes, it really helps. Thank you for the insights, Stephanie. I get the point.
Thank you, Stephanie. Thank you for the question, Yehuda. I just want to lead on from that, Stephanie, because in meta-analysis, we have the problem of preferably having the same measurement to analyze outcome measures, right? So we have to sometimes be forced to transform data into our preferred destination outcome. Will that actually affect the outcome measures, as transforming like from median to mean, or maybe from mean to median? Will that really affect it? And how should we mitigate these effects if we come across it?
So you mean how does it affect the choice of choosing either mean or median to summarize the data, or do you mean more like, does the transformation influence the values that are obtained from mean and median?
The values, the end values, does it really influence that?
Yeah, no, I mean, definitely, if you transform your data, you have to be careful, especially regarding then in the end the interpretation of certain metrics. So but that goes deeper into into the theory of statistics, because you have certain transformations which you can do, and you know that, oh, after transforming my variable that way, I know that its distribution will still be the same. So they're kind of the distribution is invariant to the transformation that you chose. And for linear transformations, which is something one very often does, right, that still works. And so my beautiful properties will persist, and I will still be able to use them. However, if you do something more crazy, like taking the logarithm, that will change the way your values are distributed, and that will then in the end change how useful the mean, for example, or the median is, because it changes the underlying distribution of your variable, so the kind of theoretical behavior of it, and hence it changes what can I do with the values that I obtain. It might change which estimator you need to use, because all of a sudden there, as you saw, we work a lot with assumptions, and maybe all of a sudden, because of your transformation, this assumption doesn't actually hold anymore, or it becomes more or less realistic. It also can become more realistic, right? And hence you're like, oh, I had this problem. Now through my transformation, I solved this problem, and now I can go ahead and use my more standard approaches, and I'm fine. but it can also go the other way around. So yeah, transformations are a little bit icky, and it can get pretty complicated very quickly, which is why I think meta-analysis is such a big topic, because you can do much wrong, but it is also very powerful if you kind of figure out how to do it.
Thank you, Stephanie. That really answers the question. Okay, anybody else have any questions for Stephanie? You can just straight up raise your hand or type in the chat box in any language you can. Okay, while waiting, I have another question, Stephanie. It's regarding the t-test. So there's one tail and two tail t-test, right? Is there a major difference in the errors between these two tests, or between the two t-tests, or is it just the same concept?
It's the exact same concept. It's just a different hypothesis that you're interested in. So for the one-sided, right, you can do, there are two sides that you could be on, either the bigger than 0 or the smaller than 0. And it just like measures, in addition to the fact that, okay, it's not, the two-sided t-test would be, it's not a 0. So we have a deviation either to the left or the right. So it either has a positive or a negative effect. But the one-sided t-test, which is, I believe, the more used one in medicine, because you're not just interested in, is there effect, but no, is there a positive effect? So that's why you would choose a one-sided test, which also gives you information about the directionality. But there's no difference in error, because they're really based on the same fundamental principle. And all you then do is look at the absolute values, basically, of your t to measure the deviation in both directions, instead of just the actual t and it being either bigger than 0 or smaller than 0 for your test.
That's perfect. Thank you, Stephanie. Okay, we have two questions. I think we can go with Kelvin first. Please go ahead, Kelvin.
Okay, thank you for the opportunity. I would like to ask to Stephanie about the sample size calculation that you have presented in your slides. Does the formula apply to all kinds of research designed? For example, the RCD1 or the cohort or any other type of research design? Because I think I've seen like different formulas used for sample size calculation. So can you give me some explanation about that? Thank you.
Yeah, sure. That is a very good question. And it is indeed true that it only applies to the t-test. And obviously also only applies to if the assumptions are met. So the thing with sample size calculation is that it is very much specific to your the trial design, and in particular the kind of properties of the variables that you're accounting for. So say you all of a sudden are interested in survival or something different, then it changes. So it's very, very likely that you've seen other things, and you always have to kind of look into what sample size calculation makes sense for the trial and the variables that you have or plan on observing. Does that answer the question enough?
Yes, absolutely. Thank you.
Thank you. For the next question, I think Wahyu has the hands up. Please go ahead.
Okay, thank you for the opportunity. Hello, Stephanie. Actually, I was a little bit late tonight, but I'm interested to ask you related to the preceding questions to power and sample size calculation. Is there any other way to elevate the power other than we just be concerned on sample size calculations? Thank you.
Yeah, no worries. I had a slide a slide for that, but no problem. You can increase power by, as we said, sample size, or by changing your properties, as in you could increase the type 1 error rate, but that's not really something one does. The other thing is that you kind of decrease the variability of your variables, which is sometimes possible, but not always necessarily possible, kind of to I don't know, make sure that your measurement device really measures more precisely, or by introducing, say, you don't just measure once, but you measure the blood pressure several times for each patient, and then kind of compute an average for each patient, just to decrease, the natural variability across the day, say. But yeah, in the end, your power really comes down to what you assume. And the power also, and that's also something one has to say, the power is very much depends on, you need to assume a certain value for your alternative hypothesis, right, in order to draw this curve, and then to determine the red area that falls below the threshold. So if you can assume different values, but in the end, it is determined by the truth. If your treatment effect is very, very small, you will have you will really struggle to detect it, and the only way to then maybe detected with higher power is to increase sample size, because sample size is in the end the only variable that you have. You can really set the sample size to whatever you want. Your treatment effect, even though you don't know it, it is kind of given by just how the drug works, right? And so in the end, there are a few things that you can do and tweak, but the easiest and most like maybe realistic way would be to change the sample size.
Okay,
Does that
thank you. I got
make
the
sense?
point. Yes. One thing that should be considered other than sample size is also variability. Is that true?
Yeah. Do you mean the variability within the data?
Yes.
Yeah, exactly.
We collect the data.
Yeah, exactly.
Okay.
That's why I said,
Yes.
you could try and make your data less variable to begin with, because that'll help you detect the difference more easily.
Okay, thank you. I got the point, Stephanie. Thank you so much.
You're welcome.
Okay, thank you. That was great discussion. I think that will be the end for our discussion session today, Stephanie. Okay, so this wraps up our session for today. It has been a very fruitful day, morning, afternoon, and night. And I hope that we can utilize this knowledge to further advance our research and impact for the betterment of the community around us, because that's really the purpose of studying. I would like to extend my most sincere gratitude to Stephanie for today's session, because we could not have done it without you. Thank you very much. And I hope you have a great weekend, and that we can meet again in future events, hopefully in person.
Thank you so much. Thank you to everyone for coming, and have a happy weekend. Yeah.
Yep. Thank you everyone for coming. Before we close our session, let's take a group photo. If you can turn on your camera, and Tifa, can you please assist us in capturing a snapshot of the screen?
Okay. Wait. One, two. Because the chat keeps opening. Yeah. Oh, wait. 1, 2, 3. Okay, I think it's only one slide, so yeah, I'm done. Thank you.
Thank you. Okay, thank you very much, everyone. See you next time. We hope everyone's well and have a happy weekend. Good night, good morning, and good afternoon. Bye-bye.
Stephanie, thank you so much. Oh my God, you're amazing. See
So much,
you.
Stephanie. For evaluation link.
Oh, yes, I forgot.
Oh, yeah.
Oh, yeah, sorry. Those who are
We
still
can
behind,
send it.
can you please fill in the evaluation link?
No, I think we can email them, guys.
Yeah, I'll
I
email
don't
them.
think it's possible. Oh, okay.
That reminded me earlier, Kak.
Okay.
Stephanie, thank you so much.
Thank you
You're
so much,
welcome.
Stephanie.
Yeah.
Thank
I have
you.
many questions. But I will directly come to your place and I will ask those questions.
Yes, please do. Please do. By the way, Aya and I, when you gave me the French macaron, Aya and I
Oh, yeah,
ate
yeah,
all
yeah.
of them. We ate all of
Is
them. Yeah. Together. It was a lot of fun.
Oh, that's
They were
nice.
very good.
You should know that there is a pastry also today, so you can come to the research building.
Oh, are you in the
What?
new
Yeah.
research building?
Yeah, I'm in a research new building.
Free food.
Yeah,
Oh,
free
nice.
food. So Stephanie, you should
Nice.
Is there a conference?
Yeah, there's a research conference here, and that's why like I'm here. Like I'm next to you right now. I'm next to
I
Fendi.
see. Nice.
Okay.
Okay. Well, it was a pleasure, guys.